Hello everyone, my name is Nahid Hossain and welcome to my talk on combating dependence explosion in forensic analysis using alternative tag propagation semantics. In recent years, the number of targeted high-profile attacks has been rising. These attacks are carried out by skilled adversaries, which makes them stealthy and remain undetected for months. For example, the Equifax breach went undetected for 2.5 months and compromised sensitive information of more than 140 million users. Most of these attacks are mixed with benign background activities, which makes it hard for the human analyst to understand the progression of the campaign. Here is a dependency graph for a 7-hour-long dataset. It contains 18 million events and raised 64,000 alarms during that time. But the dataset only contains 2 attack scenarios, making detection extremely hard. To understand an attack campaign, the analyst needs to connect all the nodes involved in the attack to generate the scenario graph. But if we just create a graph with only the descendant of the compromised nodes, the resulting graph will be extremely hard to understand, as shown in this figure. The nodes and edges are completely indistinguishable, as we can see using this approach. By performing a prioritization-based search, which is mentioned in our previous work in the sleuth paper, we get the following attack graph. Although this graph is readable, but it is still large and hard to understand without human intervention. What we want is the following compact attack scenario graph, which can be used to summarize the attack easily. In this talk, we'll be discussing how to get to this point by looking through millions of events and producing such compact graphs. We also have a demo of producing this graph toward the end of the talk. Our goal is to generate the compact scenario graphs by pruning out the benign events. One approach is to focus on the unusual events in the dependency graph. This can be learned by training on benign activities of the system. But in this case, the attacker can evade the detection system by mimicking the benign behavior and still carry out the attack. One of our main objectives is to develop pruning techniques that are resistant to any sort of evasion. On a high level, our approach is to modulate the dependency flow using subject tags. Using policy-based attack detection and root cause identification, we have developed robust techniques for assigning subject tags. We conservatively propagate all the dependency of compromised processes to resist evasion. For benign processes, we selectively propagate the dependency using our tag attenuation and tag decay techniques. We ran our experiments and evaluated our system on the DARPA transparent computing dataset. The datasets contain realistic adversarial engagements consisting of attacks using stolen credentials, in-memory payloads, etc. Next, we are going to talk about how we use these tags in our system. Subjects or processes have 2 types of tags, subject tag and data tag, whereas objects such as files, pipes, network can only have data tag. Subject tags can be either suspicious or benign. A subject with a suspicious tag can be considered to have been compromised, for example, running a malware. A subject with a benign subject tag is considered to be benign, but may contain vulnerabilities that can be compromised. There are 2 types of data tags, integrity and confidentiality. A subject or an object having a data integrity value between 0 and 0.5 is considered to have low integrity, and anything higher is high integrity. For confidentiality, it is the other way around. That is, value between 0 and 0.5 is considered high confidentiality, which means the subject or the object contains sensitive information. In the default case, tags flow in the direction of the information flow. For example, in case of a write, we take the minimum of the data tags for the subject and the object and propagate to the object. For read, we do the same thing, but the data tag is propagated to the subject. But this default case leads to massive dependence explosion, which in turn leads to unreadable scenario graphs. To mitigate the dependency explosion, One of the techniques we introduce is called tag attenuation. Our key observation here is that object serves as an imperfect vehicle for propagating malicious behavior. An attacker cannot control the output of a benign subject that previously read any high confidential or low integrity data. To capture this idea, we attenuate the writes operation of a benign subject by adding a small constant a to the data tag. The next key technique that we introduce is tag decay. Our key observation here is that if a benign process is compromised by some suspicious input, the compromise will happen soon after the input consumption. Otherwise, the input that we thought was suspicious might have been miscategorized. To capture this intuition, we gradually lift the integrity tag of a long-running subject exponentially up to a certain value with decay rate R. Also, tag decay is not applied to a compromised subject. Now let's move on to how we reconstruct the attack scenario graphs. Our goal here is to connect the low-level events and provide a compact high-level summary of an attack campaign. We discuss the steps in the following slides. The first step is detecting suspicious activities. The basic approach is the provenance-based detection policies that were introduced in the sleuth paper. The policies rely on the means and motives of the attacker. But one key problem with this is the numerous false positives generated by long-running processes. Using tag decay and tag attenuation, we're able to reduce the number of false positives by a factor. We also refined and added some new attack detection policies as well. These are the attack detection policies that we use. Mem-exec alarm is raised when a process with low data integrity declares executable memory region. This alarm helps to detect in-memory payloads. Data leak alarm is raised if a process with low integrity containing sensitive information writes to an unknown network address. File exec alarm is raised when executing or loading a file with low integrity. And here are the rest of the alarms. The next step in the attack scenario reconstruction is identifying the root cause of the attack. A key challenge here is the number of alarms raised every day. It would be impossible for an analyst to go through each and every one of them to find the actual attack scenario. We try to solve this issue by using alarm clustering. Each alarm is assigned a weight based on their false positive rates. Next, we try to identify the primary alarm that can explain the other alarms. These alarms are called the secondary alarms, and their weights are accumulated into the primary alarm. The subjects that raised the primary alarms are considered as the entry points. Now the analyst can prioritize the primary alarms based on the maximum weight. The third and final step for generating the attack scenario graph is to perform a forward analysis. We start at the entry point S, identified in the previous step. If the subject tag of S is not suspicious, we assign it to be suspicious and rerun the tag propagation. Next, we run a selective depth-first search where we don't explore the nodes with an integrity level higher than a threshold, which is 0.5 by default. The result of the output of this search is the compact attack scenario graph that we produce. The system we have developed is called MORSE. The name is inspired by the main character in the television series Inspector Morse. Our system consists of 3 layers. The lowest layer is the data consumer layer that processes input from auditing systems. The top layer is a user interface for analysts to monitor the alarms that I will show in the demo. The middle layer is responsible for constructing and traversing the dependency graph. For event monitoring and manipulation, we have developed a domain-specific language called E-star. The dependence graph operations are exposed to our E-star extensions using its runtime environment. All our tag initialization, tag propagations, and attack detection policies are written in this language. This is the entire code for our attack detection policies, which is written in E-star language. In this part of the talk, I'm going to show a demo on how we can generate the following attack graph from the dataset I mentioned at the beginning of our talk. using our user interface in Morse. At first, we start up our system by consuming one of the dataset. Our system is extremely fast. It is able to consume 1 million events per second. Next, we are going to connect our web-based user interface with our Morse system. As you can see, these are the top 12 primary alarms that shows up at that particular time. If we click on one of the primary alarms, we can see all the secondary alarms that have been clustered with it. Next, we're going to refresh the list of primary alarms. And now you can see a primary alarm that corresponds to one of the attack in the dataset. It is highlighted in red due to the high accumulated weight of the secondary alarm. Next, we're going to perform different types of search from this primary alarm. At first, we are going to perform a naive DFS. The resulted graph is extremely large and would take a really long time to render. That is why we truncated the graph for the sake of the time for this demo. As you can see, the truncated graph is very hard to understand. Now we're going to perform Sleuth's cost-based search. This also results in a very large graph, which we also truncate. Although the graph is somewhat readable, it is still too large and very hard to understand what is going on with the attack campaign. Now we're going to perform our Morse's forward search. It results in a very compact graph depicting the attack scenario clearly. From the attack graph, we can see that a compromised Firefox plugin drops a payload called GTCache in the system that gets executed. The GTCache process later gets its privilege escalated and downloads another file, ztemp, from the network. This process performs some recon and also exfiltrates the information through the network. Now we will move on to the evaluation part of our system. We have performed our experiments on the DARPA Transparent Computing Programs dataset. We tested our system on the Linux and FreeBSD data, which were collected during the third and fourth engagements. It contains various types of attack, which include very stealthy attacks such as the Firefox in-memory payload, Azazel, etc. Some attacks were performed using stolen credentials that were carried out before the data collectors were started, such as CC Cleaner ransomware, recon with rootkit, etc. Also, there were attacks that had pre-existing kernel malware in the system that can escalate the privilege of the attacker's processes. These tools were installed before the engagement started. We were able to detect all the attacks with the complete attack scenario graphs using our system. In this slide, we show our detection accuracy and alarm reduction using a wide range of attenuation and decay rates. Using our techniques, we are able to reduce the number of alarms by 11 times without introducing any false negatives. Only with very high value for tag attenuation and decay can lead to false negatives in our system. Morse is able to reconstruct compact scenario graphs without missing any of the attack activities. In the browser extension attack, which is the one just shown in the demo, generated only 24 nodes using our Morse forward analysis technique. On average, our system is able to generate scenario graphs that are 35 times smaller than a naive forward propagation technique. The dataset we tested our system had a total duration of 553 hours with 800 million events in total. Morse is able to consume this data and construct the dependency graph on the fly. Our system can process 100,000 to 1 million events per second per CPU. Morse uses a compact in-memory data representation technique, which on average takes 1 byte of memory per event, which is based on our previous work. For the total data set, it only takes less than a gigabyte of memory in our system. Our attack scenario generation is also very fast, as shown in the demo. It takes on average 69 milliseconds to generate per attack graph. These are some of the related works. The very first provenance-based techniques, such as backtracker, were mainly targeted for forensic analysis using external detectors, where MORSE is fully automated and have the detectors built in. Sleuth uses split integrity tags for reducing false alarms and performing forward analysis. MORSE uses subject tag to modulate tag propagation to do that. Prior tracker and NoDOS prioritizes on anomalous edges or paths to deal with dependency explosion. MORSE prioritizes based on tags without any training data. Holmes aim for a much higher level view of APTs, mapping events to high-level attacker goals. To tackle dependency explosion, their notion of path factor has the same rationale as our tag attenuation technique. But they don't have anything like our tag decay, which is the most effective of the two techniques we introduced. In summary, we developed two novel techniques, tag attenuation and tag decay, to mitigate dependence explosion. We also developed a forward analysis technique to generate compact graphs. We demonstrated the effectiveness of these techniques on realistic adversarial engagements. By treating suspect processes in a conservative manner, our system, MORSE, can be evasion resistant. With that, I want to thank you for attending the talk and will be happy to take any questions. Thank you.